This is the first question of today's lecture. Let's read the question at first. So, engine oil at 60 degrees centigrade temperature flows over the upper surface of a 5 meter long flat plate. So this is the plate. You can see flat plate. The length is given 5 meter, and the surface temperature of the plate it is 20 degrees centigrade. It is given in the question. You can see here the temperature is 20 degrees centigrade and the velocity is 2 meters per second. If you look at this picture, it will tell you the whole story, actually what is happening here. So this is the free stream velocity, 2 meters per second, and the atmospheric temperature is 60 degrees centigrade, T infinity. This is the leading edge of the plate, and this is the trailing edge of the plate. So we know the surface temperature, Ts. You see the As. This is actually the area, the surface area, and Q actually we need to calculate the heat transfer rate. So here, what sort of information we know? We know the length of the plate. Okay, so the plate length. We know the surface temperature. We know the velocity, free stream velocity, and atmospheric temperature. What we need to calculate is we need to calculate the total drag force, okay, and the rate of heat transfer. Keep this information in your mind. It is for per unit width. So sometimes we solve some problem, okay, calculate some other values, maybe the rate of heat transfer for per unit length. So you guys are familiar with this term, per unit length. So here you can see we need to calculate for per unit weight. So the engine oil, it is flowing this way over the upper surface of the flat plate. It is 5 meter long. So as we said earlier, when we solved some other problem, if you think about the past weeks, so we always write down some assumptions and then we calculated properties. We extract properties from the table and then we start analysis. So we'll do the same thing here. So let's say the assumptions. So this is, we will consider this is steady. The flow is steady and incompressible because the fluid is while here. The liquid, this is while, so it is incompressible. So this is our assumptions, and the critical Reynolds number 5 and 10 to the power 5. We know this is actually constant. The critical Reynolds number is 5 and 10 to the power 5. Alright, so now we will calculate the properties. So here we're doing something new today. So far when we solved some heat transfer problem, we didn't calculated the average of the film temperature here. Actually what happens, we discussed during the lecture. Suppose you have a flat plate like this. So far you already know the boundary layer concept. So this is a this flat plate, it's not moving, so the velocity on surface is 0. So, and the boundary layer, how this boundary layer creates, we discussed last week and you already know. So when it creates boundary layer, all of you know the velocity here is 0. Then the velocity increase gradually, and after a certain point velocity becomes stable, so no more increase. Then it's become equal to the free stream velocity here. So we usually say, okay, maybe this is the boundary. So we say this, up to this point the velocity will increase, and after that it is constant. So if the free stream velocity coming here, u, the velocity, it will be here equal to the free stream velocity, which is 0.99 times of the free stream velocity. That what we said last time. So what we can see, why I am telling this one here. So when it is a surface and boundary layer creates, you see the temperature varies through the surface, and the temperature is not constant actually, and the other properties. So if you go far from the surface of the plate, you will see the properties will vary. So if you consider, so due to this actually, so yeah, we should explain a bit more, but definitely I will not do it here because it will only increase the length of the videos, but I've already discussed it in my lecture. So as the temperature, and the other properties usually varies, so what we will do is we will calculate the average temperature, and our assumption is the properties will be constant with this film temperature. This temperature is actually called the film temperature. We discussed during the lecture. So we calculated the film temperature, and it is actually the average of the surface temperature and the air temperature, because we know the surface temperature, air temperature varies when the thermal boundary layer generates, and due to this thermal boundary layer all the properties will vary. So we need to calculate the film temperature, and our assumption is at this temperature, film temperature, the properties will be constant for the whole system. So that's our assumption actually. So what I say, this calculation is not 100% appropriate, so accurate. We can say this is approximate calculations. So let's go. So we calculated the film temperature here, which is 40 degrees centigrade, and now at 40 degrees centigrade, from table A3 we 13. So A13, we calculated the density, the Prandtl number, and the thermal conductivity and kinematic viscosity. All these values we got from the table A13. So this is available in your appendix. So now we have the question. The first part of this question is we need to calculate the drag force, and then we will calculate the heat transfer, rate of heat transfer. So when it is the drag force, so far we know the expressions for the drag coefficients, how to calculate the drag coefficient. So here let's solve this question. So when it is a 5-meter long plate, let's check whether the flow is laminar or turbulent. You know what I mean? So you have the plate like this here, it is 5-meter long, so the flow is, the oil is flowing over the top surface of this plate. So we don't know actually what is the flow regime, the flow pattern, whether it is laminar or turbulent. So this is really important. So we need to check whether the flow is laminar or turbulent, and you know the concept, how to do it. To check the flow characteristics, you need to calculate the Reynolds number. So that's actually you need to do every time when you will solve any problem for heat transfer. You need to check whether the flow is laminar or turbulent, because for laminar flow you have different formulas. For turbulent flow definitely have different formulas. So we will calculate the Reynolds number, and we know this Reynolds number actually depends on many things, but here when it is this plate, it will depend on the length of this plate, okay, and how is the free stream velocity, and it also depends on the density and dynamic viscosity. But here we will use the kinematic viscosity, and we know the relations between dynamic viscosity and kinematic viscosity. So we use this kinematic viscosity. So let's say here the Reynolds number is PL over nu. So the velocity, free stream velocity, is 2 meters per second. The length is 5 meters, and the kinematic viscosity is this. We are calculating the Reynolds number here at the end of the length. That means at 5 meter. So initially this is the leading edge, this is 0 meter, this one is 5 meter. So we are calculating for this length 5 meter. That means it is just at the end of this plate. So we found at the end of the plate the Reynolds number is 4.024 and 10 to the power 4. If you can remember, guys, we said the critical Reynolds number is 5 into 10 to the power 5. That means the flow will be turbulent when the Reynolds number is 5 and 10 to the power 5. And if it is less than this value, then it will be laminar. Here we found this Reynolds number at L, it is less than the critical Reynolds number. This here, it is actually the critical Reynolds number. So now, if it is less than this value, then we can say, okay, the flow is laminar. So that we said here, the flow is laminar over the entire plate. So now what we did, we calculated the friction coefficient. So you can ask me why you need friction coefficient. So let me go a bit further. Like let's say here, the first question is, see, we need to calculate the drag force. We know the formula for drag force. It is actually the coefficient, the friction coefficient, or you can say the drag coefficient, and the area, the density, the velocity square over 2. So that's actually the drag force formula. You can see this formula from your book. It is available there. So this is actually how to calculate the drag force. So here you can see, guys, we already know we can calculate the area easily because it is the plate, we have the length, and if you can remember that in the question it says per unit weight. So that means the length is 5 and the weight is 1. So this is actually area. 5 into 1. This is actually area. So that means we know the area. Density we calculated from the table. We know the velocity. So what we don't know is the friction coefficients. Alright. So we don't know the friction coefficient. So this friction coefficient formula is different for laminar flow and turbulent flow. So for laminar flow, the friction coefficient formula will be different. For turbulent flow, it will be different as well. So that means when you are going to calculate the drag force, the first thing is calculate the Reynolds number and check whether your flow is laminar or turbulent. So now we found the flow is laminar. And now calculate the average friction coefficient, CF. And this is the formula for laminar flow. 1.33 Reynolds number and the power of negative 0.5. So we already calculated the Reynolds number. So substitute this value here and then you will get the friction coefficients. So from the formula, actually this is, you will see in your book maybe sometimes this drag force, it is equal the drag coefficients CDA rho V square 2, but here I wrote it is CF. In this case, actually the drag coefficient CF, or the friction coefficient CF, and the drag, this is friction coefficient and this is the drag coefficient, this is equal because the pressure drag is 0 here, so we got no pressure drag with the value, the magnitude is 0, so we can write it as CD equals CF. So we just write it like CF, and then we know CF, we know the area, it is 1 into 5. The density we got it from the table A13. We know the velocity 2 meter per second square and over 2. So I already explained the area. So this is per unit. We know this is given in the question. So we got this is the drag force. Okay, so this is the first part of discussion, the drag force. I got it. So now the second question is, you see actually convection is happening here because of this is the solid, and we know the air temperature is given, the atmospheric temperature flow is going this way. So this is actually the convection from this convection heat transfer is happening here. So we need to calculate the rate of heat transfer. So now we will calculate the rate of heat transfer for the entire plate. Okay, so when you understand that this is convection heat transfer coefficients, and then you know for convection heat transfer coefficients, so for convection heat transfer, if you calculate the rate of heat transfer Q, you know it is equal, hence the formula A and delta T. So this is actually the formula, you know. You already used this formula for many problems. Here, actually this delta T, it is the temperature difference, the surface temperature and this atmospheric temperature. So keep in mind guys, temperature difference is always from high temperature to lower temperature. How you will calculate, it's not 20 minus 60, it should be 60 minus 20. So we know the delta T and we know the area, right? So if we want to get Q, then you can see this is the unknown, Hase. Hase is the unknown here. If it is the unknown value, then how we can get this Hase? It is actually the convection heat transfer coefficient. You know the Nusselt number formula. So the Nusselt number formula is, it is equal, you know, the Hase, the convection heat transfer coefficients, the length or the the length, the distance, and the thermal conductivity, isn't it? We know this is the formula. How to calculate the Nusselt number. This is the general formula. So for this question, if we calculate the Nusselt number, so if we can calculate the Nusselt number, then we already know the length and the thermal conductivity. This is also known. So then we will get this Hase, and then we will be able to substitute this value here. So now guys, we know the Nusselt number formula from the theories, the correlations for the Nusselt number for laminar flow. When it is the laminar flow, we already know the Nusselt number correlation. So it is 0.664 into, if I can remember, it is Reynolds number half, and the Prandtl number, I think it is 1/3. So for laminar flow, the correlations is this. The Nusselt number correlation is this. So that means we already know the Reynolds number here. We already know the Prandtl number from the table. You see, we calculated the Prandtl number, every values. So we know these values, Prandtl number, Reynolds number, then we will get the Nusselt number. So once we have this Nusselt number, we will substitute the value here. We know length, we know thermal conductivity, so we'll get Hase, and then we will substitute Hase here, and we will get the rate of heat transfer, right? So let's do that. So at first what we will do, we will calculate the Nusselt number by using this relation, then we will calculate the convection heat transfer coefficient, then Q. So yeah, so look here guys, what I did, we know the Nusselt number, general formula, which is also equal to these correlations. So substitute the value 0.664, substitute the values of Reynolds number and the Prandtl number here. So we got the Nusselt number is 1913. So once we have this Nusselt number, then it is equal to this Hase L over K. So we can write Hase L over K equal 1913. So we simplified, we solved this expression for Hase, and it will be equal to the thermal conductivity into 1913 over L. So we substitute the values here, and we got this is, you need to use your calculator. I believe this is not that difficult. So we got the haze, it is 55.25, and once we have this convection heat transfer coefficients, then we use this formula, which is haze AS and the delta T. So I already explained it will be 60 minus 20, the temperature difference. Some of you may write it is 20 minus 60. So that will give you a negative value. So you can't do that because um, the temperature will always go from the higher temperature to the lower temperature. So when you will calculate the difference, the temperature difference delta T, always write the higher temperature, maximum temperature at first, and then the minimum temperatures. That's the formula. And we know the area. This is for the the per unit weight, and this is the haze, the convection heat transfer coefficient. So we got the rate of heat transfer. So that's it. So what we did, initially, we calculated the drag force, AFD. So for AFD, we calculated the friction coefficient CF for laminar flow. So once we have this, then we calculated the Nusselt number, then the convection heat transfer coefficient, and then we got the heat transfer rate. So this is the first problem. So try to find out some similar problems like the flat plate, okay, and this is only for laminar flow. So and it's only the laminar thermal boundary layer. So in some cases, maybe if you have this plate, maybe 20-meter length, this is 5 meter, let's say up to this is 20 meter, so the flow could be turbulent here or here, so it should be a mixed boundary layer. So try to find out some questions something like that for mixed boundary layer problem. Alright, so that's all.